Okay, so we were talking about this idea of geometric interpretation of the Bayes and minimax estimators. And just remind you, the idea was that working in this finite parameter space, we identified the risk function with a vector, and the set of all possible, let's say, randomized rules. If you consider the set of all possible randomized rules, this vector carves out a particular set as the image of that set of randomized decision rules. And that set we called S. And this turns out to be the convex hull of the set of risk vectors carved out by deterministic decision rules. And so it's a convex set. And so we talked about how randomization can achieve like anything in the line segment. So any risk vector in the line segment of two, between the risks of two estimator can be achieved by randomizing, by an estimator that randomizes between those two. In any case, so the minimax problem is this problem of minimizing the decision rules, the maximum over all the parameters of this risk, the frequentist risk, and this can be written, so this maximum risk, so the risk is like maps to this y, s, for any estimator we have a y, and so the maximum maps to this infinity norm. And the minimax problem is to try to minimize this infinity norm, which has a dual form in this. Like you can see it in this line. The infinity norm can be written as the maximum of a linear function over. Maximum linear function lambda, let's say, over the dual, the unit ball of the dual norm, which is L1 here. And because the risk in our case is non-negative, the L1 norm is equal to 1, is the same as the following. So after some arguments, we basically arrived at this problem, which is roughly like a linear program problem. Almost a linear program. That's not exactly. So this part is linear, this part is linear, this is potentially non-linear, but very close to a linear programming problem. And so if a strong duality equals, I can reorder or switch the order of min and max. And what I would get is maximum for these probability space, minimum over this. Let's say y now. Let's switch the order. And so this problem we recognize as the Bayes problem. So lambda times y is the inner product is the Bayes risk of the associated estimator. And then so we find the optimal Bayes risk for the particular prior lambda that we're working with, and then we maximize over lambda. That would be the alternative dual form of the next problem. This problem is really basic. We find a prior basically that maximizes the Bayes risk or the optimal Bayes risk. And so that prior is called the least favorable prior because it's least favorable. And so the problem of the dual problem of minimax is finding the least favorable prior. So we went over like the geometry of the problem, which I'm not going to repeat. So one thing to note, which might not be clear, but it's really easy to actually verify, is that this strong duality is going to hold, and everything that we talked about works out if you can find a Bayes rule, a Bayes estimator associated with a certain parameter such that the maximum risk, this guy, matches the Bayes risk. So if you have an estimator for which its maximum risk and its Bayes risk, so this one, basically lambda y is equal to the maximum risk, then all of this goes true. Okay, so this part doesn't require you to rely on external considerations of strong duality. This one I didn't talk about, but maybe I just want to maybe go back and point out that this is a result that we sort of skipped over. So if you go, right, so here we introduce the minimax criteria, and so this was our previous notation. The Bayes rule is one that minimizes the Bayes risk, and so this is the optimal Bayes risk, and this delta lambda is the Bayes optimal Bayes rule, let's say for that lambda, and then least favorite prior is prior that maximizes it. The prior, the capital lambda is the distribution. It's equivalent to that small lambda. So here's the minimax sort of theorem. Then you put like sufficient conditions. So if assume that these conditions hold. So delta lambda is Bayes, and the Bayes risk of this estimator matches its maximum risk. So in other words, in our previous notation, so you have this lambda, and then you have, let's call this delta lambda. This has a certain risk function, which if you want, we can write it as, so this is the optimal Bayes rule. So let's call this y lambda. And so we have a maximum risk associated with this estimator, which is that, and we have the Bayes risk associated with this, which is this, really. Okay, and if these two are the same, so if there's equality, if the minimum, sorry, basically this is an average, this weighted average is the same as the maximum risk, then it turns out that the lambda has to be least favorable, and delta lambda has to be minimax. Okay, and you don't need to go through the argument that I did. You can just argue for first principle. So if you have a Bayes rule for lambda, and the Bayes risk for that, which is the optimal Bayes risk for this prior, happens to be equal to the maximum risk of that estimator, then that estimator is minimax, lambda is least favorable, and it's also going to be unique. Minimax if it's a unique Bayes estimate, which we briefly mentioned. So if it turns out that delta lambda is the unique Bayes estimator, then it's the unique minimax estimator. So do I want to argue this? So the argument is very simple. So basically the idea is that maybe you're not familiar that much with this notation because I introduced the other notation, but the main idea is that the maximum risk of the estimator is an upper bound on the average risk, which is the Bayes risk, because this is the weighted average, this is the maximum, and so we always have for any estimator that the maximum risk is bigger than the Bayes risk, which is bigger than the optimal Bayes risk, because delta lambda is optimal. Sorry, this is this part is because the Bayes rule is optimal, so this is the risk of the minimum risk for that prior, and so this part is optimality of the Bayes. So optimality of delta lambda for Bayes risk, and this one is true always for any estimator. The max is always, so the maximum of a bunch of numbers is bigger than the weighted average. That's sum to 1 with the weight that's sum to 1, and this one is by assumption. So we're assuming that for delta lambda, this is equal. Okay, so that's this part of the assumption. And you can see that this basically proves that delta lambda is minimax. So this was an arbitrary estimator. The maximum risk set with arbitrary estimator is always bigger than equal to the maximum. That, and then you can do a similar argument to show that they're basically an inequality of the same sort. Shows that, so here it's the inequality, that basically lambda would be the least favorable prior. If you pick any other prior, you would have the optimal Bayes associated with that prior is less than this quantity. Because delta lambda is not optimal for this prior. There's something else that potentially is optimal. So this is better. This is the best possible. So this Bayes risk of this delta lambda is like higher than the best possible risk. And this is less than the maximum risk. That's true always. And this is by assumption equal to R lambda. You can see that it shows that R lambda is always bigger than R lambda prime for any lambda prime. So lambda is least favorable prime. So this argument basically is self-contained. So if you manage to find, is this very clear? The notation might be a little bit tricky, but there's nothing much going on except maximum risk is an upper bound and the weighted average risk, which is the Bayes risk. And the fact that a Bayes estimator minimizes the Bayes risk, and the fact that we assume that this particular Bayes estimator has Bayes risk equal to maximum risk. So this argument is self-contained, and if you translate it to that duality that we mentioned, this proves a strong duality. So if you can find such case, you can go through that argument that I mentioned and prove that min-max is equal to max-min. Okay, so it's sufficient for a strong duality. So if you manage to find something like that, you don't have to worry about conditions of minimax holding. Okay, that part I'm not going to argue, but I'll let you figure that out. Okay, but this is a general result holds in not finite parameter spaces. As you can see, there's nothing here that requires finite parameter space. It's not necessarily it's not a necessary condition, but it's sufficient. Okay. Does that work with people? Any questions? We'll go back to the geometry soon, but I just wanted to point out that if you find a prior that leads to a Bayes estimator who happens to have maximum risk matching its Bayes risk, then you're done because you've found the minimax estimator. And the uniqueness, I'll let you argue for yourself. And it happens that prior has to be like least favorable because that sort of should be the case. We argued it, but also follows from the strong duality. Okay, so a particular example of this is when you have an estimator. So, okay, so let's define this. The decision rule, an estimator is called an equalizer if the risk is constant. Okay, so if the risk is the same for all the parameter spaces. So you have the risk function, it turns out that it's flat. So in particular, if the Bayes estimator is an equalizer, then it's going to be minimax. Because if it's an equalizer, its maximum risk is like that flat thing. So it's like I have suppose you have a flat function. So this is R theta delta. Okay, so the risk is flat. So the maximum of a constant function, its average is the same. Okay, so for this particular one, the Bayes risk and the maximum risk are going to be the same. So a Bayes rule, which is an equalizer, is minimax. That's like a conclusion. This one is a little more tricky, but we're not going to use it. So you don't have to be, like, the risk doesn't have to be perfectly flat. It just has to be flat, maximized where the prior puts mass. So if you have a part of parameter space, the prior only puts mass here. I want the risk to be constant and equal to the maximum value over that region. Because then when I average with respect to the prior, I'm just going to see this. And the average of the risk with respect to the prior is going to be equal to the maximum risk. So something that behaves like this, I could go down here. But the prior like puts mass here, and over the region where I put mass, the risk is maximized. We'll have this property. So we're not going to use this much. This is more general. This is easier. Okay. Questions? So this case A, equalizer Bayes, is geometrically something that came up last time. So when I have the risk body and I'm trying to solve a minimax problem, I have these have squares that they move. These are the level sets of the infinity loop. And it happened that often I hit this boundary at this corner. So this corner is like things that are in the 45-degree line are equalizer fields because they have the same risk. Right. So in here, this function just has two values, the two coordinates and the two values of it. So an estimator with equalizer should pick the risk size on the 45-degree line. So anything on the 45-degree line is an equalizer. Okay. And so then part A is saying if you find an equalizer rule, which is also Bayes, then it's minimax. So from the picture, it sort of should be clear, but you'll have a better picture here.
What is the X and Y?
So X and Y is R theta of delta. This is R theta 2 of delta. So these are the two coordinates of the risk. So we have a parameter space which is theta 1 and theta 2. So risk function is really specified by two numbers. That is what we call like rho delta. Okay, so this is the space of risk, or risk vectors. So let's say the convex hull of it, that's an S. I move this square up and down until I hit the boundary here. And where I hit the boundary specifies the risk of the minimax estimate. And if it happens that I'm hitting at this corner, then this is also an equalizer. So we're in the situation where we have an equalizer minimax. And then the rest of the implications of this picture we talked about. So there is this face, which is the face basically is all the Bayes rules, the risk of all these rules. Because, the Bayes rules are obtained by like moving these level sets of these linear functions. So the Bayes just associated with a particular lambda is just a linear function, and these are the level sets. And so I move that until I get usually the boundary here. And so these points that I get at the boundary are the Bayes rules. And one of them often is the minimax. So the minimax one is like a sweet, occupies a sweet spot. So this point is both Bayes and minimax, and it happens to be an equalizer in this case. So equalizer, minimax, Bayes. So it's like a very special kind of estimator. Okay. Yes.
And equalizer isn't guaranteed. It's just.
It is not guaranteed now. Yeah, but
it can be on like a set that's that number.
yes. It's not guaranteed. We're saying if you can find an equalizer rule, and if it happens to be Bayes with respect to some prior, then it would be minimax. But it's not this.
And equalizer is
I'm not sure. I can't say for sure. If you can prove it, you're welcome to prove it. I don't know.
So
Yeah.
equals to just any point on the 45-degree.
Here, yeah, any point on the 345 degree here, just the risk of some equalizer.
So there's only one on that line. That is fixed risk.
That's Bayes, yes. In this case, there is one that's Bayes. Yes. That happens to be the minimax as well. It could be a situation could be more complicated. I don't have an example, but if we have an example, we like talked about this last time. It could be like, so I touch the risk body at this point. Okay, so this is no longer equalizer. So it's a minimax rule that's not an equalizer. It's not necessarily always the case. But if it's the case, it would be like still most likely in this case, still going to be a Bayes rule. Say it's not perfectly flat, maybe it's like that. I don't know. Yeah, it would be nice to have good examples. I don't have this. This is for a particular example that I'm going to show you. These are. I'm going to give you the example, but this is a real example. But it's actually the two-parameter Bernoulli case. Okay, sounds good. Let me do the example and then like go back to the admissibility and just wrap up this video. So we can do it for this special case here. So I have the Bernoulli, just a single Bernoulli value, 0 or 1. Quadratic loss and theta is in 0 to 1. So I'm estimating just this theta, and so let's say I put a prior on this capital theta, right? Capital theta, I'm thinking of prior. I put a prior on theta. Any prior put on theta basically is a distribution of 0 to 1. And so we'll have a prior mean and a prior second moment. So these are specified as M1 and M2. Okay, these are some numbers. And it turns out that I just need these two numbers, the particular prior. Like we care about the prior as far as these go. So in any case, so you write down the frequentist risk, which turned out to be this. So why the frequentist risk of delta looks like this. Delta is like it's something from x to r, or from x to 0, 1. And because x only takes 0 and 1 values, so I can equivalently represent delta as delta 0 and delta 1. And so I have like a vector. So the decision rule is a vector here. Tells me like if I observe 0, what is my guess for theta? If I observe 1, what is my guess? And so if that's the case, then this is just the expectation, right? Of theta minus delta x. Or you can say delta sub x if you want. Squared. So theta minus delta 0 and the probability that I observe 0 is 1 minus theta. And then delta 1 minus theta squared and the probability to observe 1. So this is the frequentist risk. I rearrange it, selected like the term in theta, or let's say the coefficient, collective terms that have the same power of theta. Theta squared times something plus theta times something plus the constant. So basically, a polynomial. The risk is a polynomial in theta. Okay. And then I can compute the Bayes risk by just plugging in theta here, capital theta, and then take the expectation. That's one way of computing the Bayes risk. Plug in capital theta, take the expectation of both sides. These are constants. Okay, so these come out, and I get the expectation of capital theta squared against M2, and then expectation of theta is M1. Right. So plug in theta here. capital theta, take the expectation, these are constants, come out, and you get this expression. Okay, so that's the Bayes risk. This is the frequentist risk. Okay, so far so good. Yeah.
When we go upwards, so the base decision, the delta 0, delta 1.
Or that's not the Bayes, that's just a generic decision.
Generic decision. Does that mean when we observe zero, like this is our delta 0 means this is when we believe about theta.
Yeah, so that's your estimate of delta 0 is your estimate of theta if you observe 0. Delta 1 is your estimate of theta. They say delta, the estimate of theta, both are estimator of theta, right? But under different observations. The decision rule tells you, given any observation, what is your estimate? Right? It's just a function, but in this case, because the input space has two, they take two values, it's just really a vector, right? We can specify the Bayes rule by minimizing this. You also know that it minimizes the posterior risk. You can do it that way, but because I have like a closed form solution here, I can try to minimize this with respect to delta 0 and delta 1. And if you do that, you can, for example, take derivative, say equal to 0. It turns out that these are the values. Okay, so it's a quadratic function. Differentiate say equal to 0, you get that. This turns out to be the same as if you followed the procedure, the general procedure of minimizing the posterior risk. But it says whatever the prior moments are, these are based on the prior moments. What will be an equalizer rule here? Equalizer is the one that has risk, which is constant. So how do I get a general equalizer rule? Frequent, I want the frequentist risk to be flat. Yes.
Delta 1 minus 0 equal.
No, I want the risk to be equal for all theta.
So if the
Take the derivative, say equal to the, there's an, okay. So if it's flat, then it's constant and derivative of all orths. So you can take the first derivative, say equal to 0, second derivative, say equal to 0, third derivative, whatever. So it's a polynomial. So it is a polynomial constant. Polynomial function. Constant if these are 0. Otherwise, if I have any theta there, it's gonna. So I have to set this equal to 0, set this equal to 0. It's equivalent to set x, taking the derivative and set it equal to 0 for derivative like order 1 and order 3. Then it would just be like this, just constant. So you set this equal to 0. So this equal to 0, it gives you two equations and you solve. And it turns out that there is only one. So these are the two equations. There's only one equalizer rule. Okay. They're not multiple, that this is the only equalizer rule. Now I want an equalizer rule, which is also Bayes. So this is the general form of a Bayesian estimate, a Bayes estimator. This is what an equalizer looks like. So I'm going to look for a prior that allows me to do that. So I set these two equal, M2 over M1 equal 1/4, and that thing equal 3 over 4, and solve for M1 and M2. That gives me M1, the optimal M1. This is the moments under the least table. So M1 should be 1/2, M2 should be 3 over 8. Then I'm going to look for a prior that has these moments. And I'm in luck because like beta 1/2 has these moments. Okay, so after all this work, we can say that this is least favorable because of our theory. Least favorable prior, the Bayes rule associated with this, which happens to be an equalizer, is also minimum. So the decision rule is the same. This is the decision rule that's minimum. But we can for sure say that this is minimax. Okay, so the minimax estimator, in this case, if you flip a single coin, it doesn't produce 1/2. So it just says if it's 0, guess that it's 1/4. If it's 1, guess that it's 3/4. But that's how you do minimax estimation with a single coin flip. Okay. It's something non-trivial. And then you can calculate either the maximum risk or the Bayes risk. It will be the same, it will be 1/16. It's like plugging into this, either this or that, because the Bayes risk and the maximum risk are the same. And like everything's flat, basically, there's just one value of risk. So it has a constant risk of 1/16. Is this sort of clear? As an exercise, there is this part which I skipped. So you can calculate the Bayes risk. Well, Bayes estimator has, because we're under product, a lot of the posterior expectation. Okay, you can do that, and this will be posterior expectation. It has the same formula. You can just verify for yourself. This is for a generic prime. But if you have questions, now is a good time.
Just sort of possible. To explain. Orally is accurate.
What do I need to explain?
The
M1 and M2 are the moments of the prior. Okay, so you have a prior distribution of theta. That prior distribution has a certain first moment, the mean. And it turns out that those are the only characteristics of the prior that we care about. Or, as you can see, the Bayes rule is defined in terms of those two numbers. So you put any prior on theta, the associated Bayes rule is this. This you should be able to calculate in different ways. Okay, so you have the tools to be able to calculate the Bayes rule. The equalizer in this case is sort of easy because you can write down the generic of the risk. Recall this is for a generic estimator. And then like looking at it, you can see that the only way it's going to equalize that is that these coefficients are 0. So set them equal to 0, and it turns out that there's just one solution. Okay, so this example can be extended. We're not going to do it, but if you have IID Bernoulli, it turns out that by some sort of similar argument, theta under 2 would be favorable, and it leads to an estimator which has like a flat risk. The risk, the minimax risk is this number. If you compare the risk of the sample mean, which is theta times 1 minus theta over n, so like asymptotically, it's not that different. So like at 1/4, this guy goes from 0 to 0, right? At 0, it's 0. At 1, it's 0. This is the sample mean. At 1/2, it's maximized, which is 1/4 n. The minimax one is slightly lower, as you can see. So if I drop this 1, it will be 1/4 n. Then it will slightly smaller, but not by much. So this is going to be the risk of the minimax estimator. So minimax estimator is like this, slightly lower, so it has this better maximum risk than sample mean. But the gap goes away.
This doesn't depend on theta. The minimum risk.
No, this is like an equalizer. So the risk is flat. Yeah.
I just want to make sure that the technique you got to get the least favorite pattern.
Yeah.
So are we utilizing the fact that equalizers, Bayes solution equalizers minimax?
Yes. So if you have a Bayes estimator, which is equalizer, then it has to be a minimax.
We can do that in this case. We can find equalizer solution.
You can look at all the possible equalizers, which happens to be just one. So if there is any Bayes equalizer, it has to be this. Then we're going to look for a Bayes rule that is exactly this. And it turns out that there is a Bayes rule. So we have to find a prior that uses these as a Bayes rule. This might not be a Bayes rule. But if it turns out to be Bayes with respect to some prior, then you're done. There's another example, which is if I change the same problem, but I change the parameter space, this you can do in the whole problem. There's a solution here. But if I just, for example, do 1/3 and 2/3, these are the parameters that I want. look at. I just know that the probabilities are one of these two. Then in this problem, there are many equalizers. Yeah, but the equalizer is not a single one. And in this problem, the minimax would be different. Okay, so it would be very much dependent on this, but because of the very sort of large parameter space here, we just have one equalizer. If your parameter space was smaller, you could have multiple equalizer rules, then you'd have more leeway. And this is the only example that I'm going to do of minimax. And you can see it's pretty interesting. Like just one Bernoulli is a lot of work to figure out. So you shouldn't be able to, or you shouldn't expect to be able to find minimax estimators easily. What people do in practice is just care about the minimax rate. So things that behave like minimax asymptotic. So this is minimax optimal in terms of rates. So the rate it's achieved is the same as the minimax estimate. So it goes on 1 over n. This is also going down on 1 over n. This is good enough in practice. The exact minimax rule is hard to find. Sounds good. Any other questions? So this follows from this result, which we can just go through. I did it rather quickly, but the argument is very simple. If you find a Bayes rule whose Bayes risk is equal to the maximum risk, then it has to be minimax. And the prior associated with that Bayes rule has to be least favorable. This is the only result that you're going to need. Any other questions? So the punchline is we look for minimax estimators, if at all, among the Bayes rules. Okay, that's where we look for. Just have to find the right prior. If you find the least favorable prior, that Bayes rule is going to be. Okay. This one really nice.
One question about the terminology. So you said minimax estimator. Would that be so in that case, is that Bayes rule? Like this is Bayes decision rule? The constant equalizer is minimax.
No, there is oftentimes the minimax, there's no prior associated with minimax. So there's a minimax, there could be multiple minimax rules, but let's say there's a unique minimax. So there's a minimax rule or estimator if you want. Okay, there are many Bayes rules, so rule is the same as estimator if you want. Decision rule is the same as estimator. I'm using them interchangeably, yes. Yes.
Decision rule is equal to estimator.
Decision rule is a synonym or synonymous with estimator. Decision rule is the decision theoretic terminology. So when I say rule, I mean decision rule, not the classical way. So Bayes decision rule or Bayes estimator. Okay. The objects that we're looking at, they're just of one kind. Either call it decision rule or estimator or whatever you want to call it. Other questions? Okay. Back to this setting. So this I talked about the finite parameter case. And in the finite parameter case, so there is this result. We talked about the admissibility. That's the last thing that I want to maybe I just emphasize. In the finite parameter case, basically can show that admissibility and Bayes are basically the same. So an estimator, if you have a Bayes rule or a Bayes decision rule, you have a decision rule which is Bayes respect to some prior. Let's say if all the lambda i's that prior are bigger than 0, that's a discrete case. So it puts mass, the prior puts mass in all the points in the parameter space. Then that decision rule is admissible. This is easy to show. The thing that we discussed last time is the opposite, which is if you have a finite parameter case and delta is admissible, then it has to be Bayes respect to some prior. This is much more interesting. It says that the class of admissible decision rules is covered entirely by the Bayes rule. So there's no admissible estimator that's something else. Okay. These are called sometimes complete class theorems. Okay, so describe the complete set of all admissible decision rules as basically essentially the Bayes rules. Geometrically, we see that this is true. Okay, and the intuitive idea behind the proof is if I take the risk point, the risk of an estimator here, or like pick an estimator or decision rule, this is the risk associated with that. I can easily geometrically see if it's admissible or not if I form this like code. And if there's any other estimator in this code, then it makes it admissible. So we need to move this all the way to the boundary basically. So for an admissible estimator or for an admissible decision rule, this code does not intersect this body except at that point. So if I exclude this point, so that's this idea here. So for any x, let's say x is my candidate decision rule, I form this set, the set of all y's whose coordinates are less than or equal to xi, except for xi. So I exclude xi. So that set is still convex, and the risk body is convex, and they're disjoint, so they can be separated by hyperplane, and this hyperplane will have a normal. That normal defines the prior risk. Because that normal has coordinates that are not negative, and you can normalize it, so normalizing the direction doesn't change the line. And because it's separating, so everything here is one side, everything is else to the other side. If you write down the implication, this is saying that the Bayes risk this is smaller than the Bayes risk of all the other things. So this is the Bayes risk. Okay, because the Bayes risk is basically just the value of cycles. Anything below here has smaller values, anything above has higher values. So this has to be the smallest Bayes. Has to have the smallest Bayes risk. So it's a very nice geometric proof of a statistical fact. Okay. Admissibility implies being Bayes or Bayes rule is a consequence of this hyperplane or the separation result in convex analysis. So that's the only remaining part of this discussion that I wanted to emphasize. Any questions? Comments? Yeah.
I think this is a question for the business lecture. And kind of, how do you integrate like interpart that love actually want base
Bayes risk. So the inner product of lambda and this y is just this weighted average or the sum basically. And so these yi's, if you remember, they're just the risk of the delta at different theta i's. So it's just this is that. And it's really the nature. So averaging the risk function, the risk vector. So Bayes risk is really a weighted average. So you have the risk function, you average it over theta. So that's maximum risk, maximize it. So the maximum overall theta I. If maximum risk, the average, weighted average, the Bayes risk. So if I change the weights, I get a different, the Bayes risk under a different prior. So the prior just tells me how to reweight.
Oh, so lambda is the distribution.
Yeah, lambda I is basically the probability that you, the prior probability. So in this case, we're working with, we're working with this finite parameters, but you can think of lambda I as being the distribution, the prior distribution applied to theta I. Okay, so this is the probability mass that I put on. The probability mass that I put on theta I. So prior distribution on this is specified by the PMF. This is like a PMF about the mass. Okay. Are we good? Okay, yeah, so this, I think if you're interested, you can dig into this further for yourself. There's a nice, very nice interpretation of this in terms of, as you can see, like duality, convex duality. And so it's one of the other areas that the statistics needs some other very nice area of math. So we saw like a bunch of this in exponential families. So convex analysis meets statistical models. This is convex analysis meets Bayesian inference or decision theoretic inference. And a lot of the, like you can see, like geometric interpretations have meaning. So one problem is solving this maximum, like minimax problem. The other is the Bayes problem. And there's duality, there's this least favorable prior, there's admissibility, separation of convex sets. So all these ideas sort of interplay. There's a very nice type of kind of domain to think about. Okay. So with that, we're gonna switch to another topic, which is gonna occupy us for next couple of lectures. So we're basically almost done with all the things that we started to like or set out to do. So we started decision theory and we had all these complications. So we sort of, let's say, to a satisfactory degree, resolved them, okay, to a certain degree. But the issue, as you can see, as it came up, it's very difficult, for example, to do to analyze finite sample problems. So, for example, UMVUs exist potentially, but they're hard to find. Or the complete sufficient statistics might exist, but they're hard maybe to prove or find. Minimax was extremely hard to obtain. So people traditionally resorted to asymptotics. So maybe if I let, okay, let's say we restrict ourselves to a particular setting where we have IID samples from a particular model. So the decision theory framework is much more general. So your model is just a model for the entire observation. It doesn't have to have this IID structure. Okay, but let's say we like restrict ourselves to a class of models where there is a base model. I'm putting like a P superscript I. So the observer, this is like one observation. We have a sample space X with these family probability distributions. And then I'm going to assume that I observe an IID sequence of observations from this particular family. So there is one thing that they take, and then I generate IID. So we take the decision theoretic framework. If I want to like, model the full problem, it's really the family is this P to the N, which is just the products of these cadence. So these are product measures. So the distribution of a vector of observations whose marginals are P theta and their IID. So that's describe the distribution of the vector. If we're going to be formal, we're working with models that look like this. But because of this IID structure, things simplify. So I can let n, for example, grow. Okay. And you know that good things happen when you have IID data or IID random variables, like let's say averages converge by the law of large numbers, you have CLT. And so all these limit theorems and probability kick in to hopefully simplify our analysis of risk or comparison of estimators. Okay. So we're going to focus on this case, and we plan to analyze estimators as n go to infinity, and the picture simplifies a great deal. Okay. So far, so good. Okay. Just wanted to emphasize that this is a restriction of the general decision theory framework. So what class of estimators we want to analyze? We're going to look at these things called M-estimators. And these are estimators that are solutions of optimization problems. And you already know one of them, for example, if you do maximum likelihood, you're maximizing the likelihood to produce an estimator. So you're solving the optimization problem. So MLE is an instance of an M-estimation. More generally, you have a family of functions from this X to R and characterized by this theta. And then you apply this function to Xi. You take the average. And this gives you a random function you maximize. Okay, so for example, if I have m theta x is equal to, let's say, log p theta of x, where, or like p1 if you want, where this is the density of this guy. I think I dropped one here. So this, if this has a density p theta of x, if I take this m theta of x to be log p theta of x, then you can see that this is the solution of this is the MLE, because the joint distribution is the product of p theta of xi's, and so if we take the log, I get the sum of logs. So MLE is a particular example. I'm going to also introduce this notation, capital M theta, for this. So this is M theta. Okay, so we maximize these things. We want to see what are the properties of this estimator. Okay. One more example. So we have seen one with it. The other is that, for example, negative x1 theta squared, that M theta would be that, and the solution would be the sample mean. Okay, so sample mean is a particular example of an MSE. If I take the M to be the absolute value, this would be the function, and it gives me the median. That I try to minimize, it gives me the sample median. So sample median is another MSE. Yeah, so these are minor points so you can ignore. But you can see, like, it doesn't have to be MLE. I can just pick a particular reasonable function that measures some sort of a distance between observations and x. So this might not be necessarily good in a problem where x is particularly theta. But I just wanted to mention that x, for example, x bar is an example of an MSE, and so on. Okay, so to have this framework in mind, we want to analyze this, but for this we have to develop some more theory. Okay, if we manage to analyze this, we can, for example, manage to analyze the MLE. That's the main thing that we want to analyze, but even more general estimators. Okay. So far, so good. So that's the plan. There are some other type of estimators that I usually talked about, but in the interest of time, I sort of omit them. For example, if you try to differentiate this, like a naive way of solving this is if the parameter space is the entire, let's say, real line or RD, is to differentiate so equal to 0. Okay, so you get a set of equations, nonlinear equations that you have to solve. These are called usually Z-estimators. So Z-estimators are solutions of nonlinear or general equations. They call estimating equations. And so you can think of M-estimator and Z-estimator as dual. So if I take the gradient of this, basically say equal to 0, it gives me Z-estimator. But we're going to focus on M-estimators. So that's the motivation. And this is the machinery. Okay, so we need the machinery of large sample theory or asymptotics. There's a separate course taught, I believe, on large sample theory. But I'm gonna do a very condensed, short, essential large sample theory. Okay, the essential part. In case you have more interest, you can follow that other course. But the basics are important, so we're going to talk about that. Hopefully, you see it multiple times, it becomes more clear. So in order to analyze the behavior of statistical estimators, we want to let n go to infinity, and so we need some sort of notion of convergence, or notions of what it means to be a good estimator. So the idea is this notion of consistency. So if I generate x1 up to xni in terms of t theta naught, theta naught is the unknown parameter, and I form these theta hat n, what I would like to do is this converges to this theta naught as it goes to infinity. So we say this sequence of estimators is consistent if that happens, but because these are random, I have to specify how they converge, and the convergence mode that we care about is convergence in probability. Okay, so P is for the probability, And here is a good time to ask how many people know about conversion probability. Conversion probability, how many people? Okay, 1, 2, 3. So what is conversion probability? Right.
So probably the deviation of the sequence from the parameter of interest, the limit of that should go to 0.
Okay, theta hat n minus theta naught. The probability. Okay, greater than epsilon.
Limit of that as in.
Okay, limit should be 0. Okay, or we will say this goes to 0 as n goes to infinity. Right. That's the meaning. So this event is a bad event. So for every epsilon, let's say we're looking at an event that this deviation is bigger than epsilon. I want the probability of that to go to 0. Alternatively, the probability of the complement has to go to 1. Right? You can say the probability of this being in the neighborhood of epsilon neighborhood goes to 1. These are equivalent. What I wrote down there, if you look at it, is a little bit more general, but the same idea. So if I have a general distance, I want the distance between theta and then theta naught being bigger than epsilon has probability that's vanished. And so this distance could work, for example, in the metric space. If these are, for example, vectors, it can have norms, different norms, such. Okay, so you can say conversion probability in a certain sense. In univariate case, you just do absolute values. We'll be happy. Okay, so everyone seems to be on board. Okay, so we want to show that, okay, so what are the conditions I put on this? And like, what are the conditions of the probability model such that this happens? So when I solve this, we say that converges to the truth. Okay, so this is a very desirable problem. And if this happens, then we can ask more questions. So how large is the deviation as we are going to 0? But this is maybe we can call it 0th order property. Then we care about the first order property, or you can call this the first order, the other one second. So how do we prove something like that, or try to show something like that? Anyone has any? Try it. Markov. It's a good way. These are good, yeah. So, like, okay. I want to like say, and just like have this up there. I want to prove that the solution of this is not going to be in general true, but let's say this is an estimator. Okay, for any sample size that I have, I can solve this and the data I have goes to n, which depends on all the samples. And as n goes to infinity, I'm hoping that this converges. I actually don't know, but I'm hoping that it converges. But because of that, let's say, for example, if this is the MLE, we expect that probably MLE is good. So let's say this is log p theta. I'm hoping that that's the MLE is going to converge to the truth. So I want to prove that. So the suggestion is to use the Chebyshev or Markov. This is good. So this is like if it was a different course, we're going to use that. Like this gives you a very precise finite sample conditions. But you can use Markov or Chebyshev to prove a result in probability theory, which we can then use. So what is the basic result in probability about conversion probability? Law of numbers. Yeah, the law of large numbers is the main tool. Okay. So you can use the Chebyshev or Markov to prove law of large numbers, and then you can use the law of large numbers here. Or if you want to control finite sample controls, you can start from the Chebyshev from the start. So let's say if this was a 200C course, you might have done something like that. But Chebyshev is used to prove weak law of large numbers, let's say. So let's just use the weak law of large number, or like law of large number. Okay. So this is a candidate for the application of law of large numbers, right? So we have an average, and these are random variables. So these are like yi's. Let's say a fixed data. Okay, so these are yi's. They're still IID because xi's are IID, right? So this will converge to something, hopefully under the weak law of large numbers. So can we claim that this converges to? What does it converge to? Sample, this is the sample mean. It converges to the expectation of one of them. Let's say if this was y1, this would be y. Like if these are yi, that's the expectation of y1. Okay. Which is just saying that this converges in probability to expectation. I'm going to put theta naught because the true probability distribution is theta naught, m theta of x1. Okay, so that's the limiting distribution, or the limiting function. So this notation hopefully is clear. So x1 has the distribution p theta naught. Okay, so each one of the xi has the distribution p theta naught, but these all have the same distribution and then the same expectations of this. And so the sample mean converges to that. And this happens to be a function of theta. Okay, so this is a new function. This is m theta, which is the limiting function. This thing we called mn theta. So we're dealing with a random function, which is converging to m in higher, like with improbability, okay, as n goes to 3. The tricky part is, this is true if I fix theta. Okay, so if I fix any particular theta, then this is a sequence of IID random variables, and it converges to that particular value. I change theta, it's a different sequence, it converges to the corresponding thing. So I can say point-wise, this sequence of functions converges to that function in probability. So point-wise means for every fixed theta, it converges. But what I care about is the argmax of this. Okay, so I have a sequence of functions. I can say converge in probability point-wise. Point-wise means I fix any theta, this happens. Can I claim that the argmax, for example, of this converges to argmax of m? If I can claim that, then I'm mostly done, because then I can study the argmax of this. And if the argmax of this is theta naught, then I've proven the consistency.
Should I just be in, right? What was?
Was there a question? Oh, yeah, it's okay, right. You mean this? Yeah. So this is the limit. That's this quantity that doesn't have any n in it. So this is deterministic quantity. So this is a random function. That's this guy. M is a deterministic quantity, like a function. So this goes to that. And the other one goes, this is the that is this random function. M is that deterministic function. So I have a sequence of functions that converges pointwise. The question is the argmax converged? Anyone? Good. Okay. So this is not enough. So pointwise convergence, even if it was like non-probabilistic, it wouldn't be enough. So you need a stronger notion of convergence. Uniform convergence would do. There is a weaker notion of convergence that would do, but uniform is good for us. So this is not enough. So for any fixed theta, law of large numbers tells you that this happens. But pointwise convergence is not enough to guarantee convergence of maximizers. So we're going to resort to uniform convergence, which says, so another way of writing, so let's write it the other way. So this is saying mn theta minus m theta converges to 0 for any theta. What we want is the maximum of this deviation over all theta converge to 0 in probability. So uniform convergence is stronger. It's saying supremum or maximum converges to 0. Okay. And if you've seen like any sort of real analysis, this is a stronger notion of convergence, which is not implied by pointwise convergence. Okay, to convince you that this is true, here's a very simple example, deterministic. So I have here a sequence of functions, MMT, that converges pointwise to a limit, but the maximizer don't converge. So these functions have like two bumps. One is fixed, like this. This is this part, and the other part, you can see like it's just if you plot it, it looks like this vanishing triangle. So as n grows, this like the base of the triangle shrinks, the height is the same. So if I pick any particular point, eventually this triangle moves past that point, and so I get this constant like 0. So for any fixed point t, there is a sufficiently large n such that this function becomes 0, or like becomes like I'm either here, which is like everything is fixed, so it's fine. Or I'm in this region, there's some dynamic, but after a while, this moves past my fixed point, and so this function is going to be 0. This is going to be 0 as well. Or I'm here, it's going to be they're matching. So pointwise, everything is fine, but you can see that the maximizer. So in the limit, there is no peak here, because in the limit, this completely loses this part. But so the maximizer of MNT is converted to 0, whereas the maximizer of MT is just at 1. Okay, so that they completely like doing completely different things. So you just completely miss this action when you went to pointwise limit. But this sequence of functions is not uniformly converging to this. Uniform convergence fails, and if it was uniformly converging, then the maximizer would converge as well. Why does it not uniformly converge? I'll let it take you to just convince yourself that it's not uniform. But this is a counterexample to show that you need a stronger, at least, than pointwise convergence. You don't need as strong as uniform convergence, but that's where we're gonna assume. So this is the result, which I'm just gonna maybe state and come back later and talk about. So we want to show this very general result that if you look at this IA-descendant, you look at the general M-estimator, and if you have this uniform convergence, so the M is that candidate that we have, and M is converge uniform with 0, and this condition, which is a technical condition, is saying the maximum. This is for the limit. The maximizers of the so basically, theta naught is the maximizer, but there's no other maximizers in the vicinity. Or the maximizers are well separated. They're unique and in a sense separate. There's no, let's say it's unique and there's no other nearby maximizer. Then these two would guarantee that theta hat converges to theta 0 as well. So this is a very nice general result. And the proof is sort of straightforward. We come back next time, hopefully, and do it. And I talk about like under what conditions possibly these would work. Okay? That's covered. Okay, thank you guys. See you.